Hi, everybody. Thank you for attending this session at SoloCon, where we'll be taking a look at the Istio and Gloo mesh security model. My name is Lawrence Godbon, and I am a field engineer here at solo.io. I've actually been at Solo for a little over a year now, and during that time, I've been working directly with several groups that are at various stages of their Istio or service mesh journey. And one of the common themes that we've noticed during that time is that the Istio security features are one of the biggest reasons why people are interested in using a service mesh, or more specifically, why they're interested in using Istio. So kind of taking that experience and kind of taking the questions that have come from that, I actually gave a talk at IstioCon last month that was entitled Deep Dive into Istio Auth Policies. So this talk is based on that, but we're also going to layer on top of that an introduction and kind of overview of how Gloo mesh will build on the Gloo mesh security features will build on the Istio security features. And so more specifically, what we're going to look at for both Istio and for Gloo mesh is the various policies and configuration you can do as a user or an operator or a consumer of Istio service mesh, and how, but more importantly, how those policies and configuration are actually translated to Envoy config, and in other words, how they're implemented and enforced down at the data plane. So let's go ahead and get started. So we'll have a quick intro of Istio security model in general and kind of how Envoy fits into all of that. The Envoy sidecar proxy fits into all of that. Then we'll take a little bit of a closer look at the pure authentication features in Istio. Then we'll take a look at the authorization policies that are available to you in Istio. And then finally, we'll take a look at the access policies that are available to you as a Gloo mesh user. So to get started, let's take a look at Istio security. So this diagram comes directly from the Istio documentation. This is a high-level overview of kind of the Istio security architecture. So down at the bottom, you have the control plane, and the control plane, will perform various features from a user or operator perspective. This is where you apply you're essentially applying your policies or configuration to more than likely your Kubernetes API server that's stored in etcd or whatever the configuration store is, right? And then that it's translated by the control plane and sent to the various proxies that are part of the data plane, right? And from a data plane perspective, as a user, when you make a request or when you have service-to-service communication, the actual request or the traffic flows through these sidecar proxies and potentially your ingress and egress gateways. So in this case where we'll look at the service A and service B, if service A and service B need to talk to each other, they're not going to communicate directly, right? The sidecars kind of mediate that communication. And then from a client perspective or a consumer, right, you're making a request into an API that lives in the service mesh, right? You can do JOT enforcement or TLS or even mutual TLS at that level, right? And that's enforced by the ingress gateway, if that's in the data path, right? And then from the ingress gateway, it can go to a sidecar proxy of service A, and that will happen over mutual TLS. And then if service A needs to talk to service B, that communication also will go through the sidecar proxies, right? And that communication will also happen over mutual TLS. For the mutual TLS perspective, in order for that to work, these service workloads need to have identity, right? And so that's one of the other features that's provided by Istio kind of out of the box, which makes it so powerful, is that when you have a workload or workload instance that starts up, you automatically are going to get a certificate provision for that workload. And so that happens because these sidecar proxies, there's another component to it, which is called the Istio Agent. And that agent is automatically runs and it's responsible for provisioning a certificate that represents the identity of this workload. And so there's a certificate authority component of Istio-D. So there's a lot of value provided here, and a lot of it is really not necessary. There's not a whole lot of configuration needed to get it out of the box. It comes for free by default. And that's what makes it super useful and super powerful. So let's go ahead and kind of zoom in a little bit on this service-to-service communication, because that's a good way of kind of understanding how this all works. So this is an example of a service-to-service call. We have a single namespace called foo, and in that namespace, we have a sleep application and an HTTP bin application. And so we want to make a request from sleep, an HTTP request to the HTTP bin app, and we want to make a request to the headers endpoint. And so you'll see in this kind of URL that we're hitting, right, it's plain text, so no HTTPS, right? It's to the HTTP bin service, which is outlined over here. And then the port 8000 is the destination port of the service, right? So kind of long story short, what happens when the sleep pod or the sleep application makes this request it's actually going to go through the sidecar proxy on the client side, right? And so there is essentially what's called a listener, and we'll get a little bit deeper into this. There's a listener in the Envoy sidecar that's going to know when you're making a request or trying to establish a connection to HTTP bin, right? And so in this case, it will go through the port 8000 sidecar, right? And then from here, the request, so again, this connection was established over plain text. Then from here, it's going to go over Istio mutual TLS to the inbound or the server side, the workload sidecar proxy, right? And that happens because these Envoy proxies can speak mutual TLS essentially to each other, right? So this port 15,006, we'll get into this in a little bit, but essentially what you need to know is that this is really the what's called the virtual inbound listener for a given workload. And so we'll kind of get into the details of how this works, but this piece is what receives the connection from the sleep application. Then the proxy is going to do whatever processing it needs to do. And then the request will ultimately make it to the HTTP bin app on port 80 because that's the target port, right? So we don't have time to go through every single hop. So what we're going to do is we're going to zoom in on this inbound kind of request to Envoy and take a look at how that actually works. So, okay, so we have a inbound connection trying to be established from the sleep pod to this is the HTTP bin incoming sidecar proxy, right? And so there's an IP address and port here, right? So what ends up happening when you're trying to request a service in Kubernetes, and depending on whether or not you were using a sidecar or you were using just regular Kubernetes networking, kind of depending on that will determine how this IP address gets kind of used as the destination. But we'll just look at the kind of the Kubernetes perspective, right? So you have a Kubernetes service, which really, the backing implementation of that service is a set of endpoints. And so this is kind of an example of the endpoints for that service, where in this case, we only have one of them. So when you try to make a request to the HTTP bin service, you really end up getting sent to this IP address. There's only one of them, so you get this 10.100.1.9 IP. And then remember, the target port was 80, so we're going to go to this IP and this port combination in order to get establish a connection to the service that we're trying to contact. And so that's represented over here, this 10.100.1.9 port 80. And so this connection is trying to be established here. Again, this is also mutual TLS traffic. And then just as a reminder, kind of from the layer 7 or HTTP perspective, this is what that request looks like. So this 15,006, what does that actually mean? So when the sidecar starts up, one of the components of really using Istio is that you inject the sidecar, but there's also an init container that gets injected kind of as like the standard Istio installation. And what that init container does is it runs some IP tables rules that essentially will hijack any packets basically that are intended for certain destinations. And so in this case, kind of at a high level, all incoming packets that are really destined for this application. So in our case, HTTP bin, everything that's being sent to it is really going to get hijacked, and it's going to be redirected to this port 15,006. And so from a listener's perspective, the listener is what the Envoy component that's responsible for accepting connections and then doing something with that connection, right? So this is the listener config for that virtual inbound. And the listener is listening for port 15,006, and it does so on all IP addresses. But the 15,006 part is important, right? Because we're redirecting incoming traffic to this specific port. And so we'll take a look at what actually happens to because we're not really using this 15,006 port, right? This is transparent to the applications, but we know that it's being redirected to it. So we know that this virtual inbound listener is what's going to handle essentially all of the inbound traffic for this application. So then once we have the connection, we need to do some processing on that connection. And the way that you do that in Envoy is using filter chains. And so you probably heard that before or several times. It's one of the kind of the main features of of Envoy is that it's kind of based on a filter chain architecture. And so kind of the simple case is that you have a listener and you have a simple single filter chain that handles the processing for that listening, that incoming connection. It's a little more complicated in Istio because we have several of these. So really you have, there's a concept of multiple filter chains, and in order to determine which filter chain to use, there's a concept of a filter chain match. And so this listener config over here kind of shows an example of that, where you have we have a filter chain match. So we have one set of filter chains, and in order to determine which one to use, we do some testing of some incoming connection properties and so on to determine whether or not this is a match. And if it's a match, then we'll use the filter chain associated with this match. And so in this case, we do have a match. We have a destination port of 80. So again, remember our destination port is 80, right? Even though the IP tables redirect happened and so on, we still have access to the real original destination, which in this case was 80. So this is a match here. The transport protocol is TLS, because remember, this is the incoming mutual TLS connection. And then finally, this application protocol section, this is necessary because Istio by default runs in something called permissive mode, which we'll get into in a little bit. But really, this is saying that, I am speaking Istio mutual TLS, even though, potentially there are other people that are speaking TLS. So it's a little, we can kind of skip over that for now because it's not particularly relevant to here. But the important part is that we have a filter chain match, right? Based on the incoming connection and the properties of that connection. So we know that given this match, now we know that we can use this set of filters in order to process that connection. Before we actually look at the filters, though, there's another component to this, which is called the transport socket. And the transport socket is what's responsible for actually performing the TLS, or the SSL kind of the SSL or TLS component of the connection, right? So in this case, this transport socket config also is defined right alongside the filters. So when we get a filter chain match, we know that we need to use this transport socket that's defined along with it, right? And so the TLS, the transport socket does a couple of things. So really in this context, what we're doing is we have this transport socket as part of our listener. So that's saying, okay, we're essentially saying that we need to do TLS on this incoming connection. But more importantly, we also are saying that we require this client certificate. We're setting that to true. So in other words, this is mutual TLS, right? So not only are we going to do TLS, but we're going to require that the client present a certificate, and then we'll actually perform mutual TLS essentially. And then what we also are providing is a way to validate that client certificate, because it's not enough that someone the client presents a certificate, right? We need to actually validate that it's a valid client certificate according to our whatever our configuration is. And then we also are going to do things like we're going to enforce that the SAN it matches what we expect it to be. So in this case, we're enforcing that it's a valid SPIFFE certificate, which is important from Istio, because that's how identity is done in Istio, right? Is kind of using the SPIFFE model as determining the identity of various workloads in the mesh. And then finally, all of this kind of so for example, the root CA, the way that we receive the configuration of the root CA, so the public cert to actually perform the validation happens over SDS, and that so that it can be done dynamically, essentially. Okay, so we covered the transport socket, and we know that that's associated with this match. Now we can actually get to the filters. So there are kind of several tiers of filter. Kind of the one that's called out here is a network filter, right? So this is what happened. This network filter is called the HTTP connection manager. There is actually more there are other filters that are part of it, but this HCM or HTTP connection manager is probably the most important for explaining what's going on. So this HCM is responsible for actually all of the HTTP type of processing that happens in Envoy. And so associated with this filter chain match is the set of network filters, which also includes this HCM. And so that HCM then has a set of HTTP filters associated with it. And so it kind of looks like this, right? So we have the connection coming in. We did the filter chain match, so we determined which filter chain to use. We also determined which TLS transport socket to use. So now we have our network filter, which is the HCM, and then we have all of the HTTP filters that are associated with it. So in this case, this is kind of a sample where we have the Istio Authentication filter, which we'll talk more about later. Then we have the Istio Stats, which provides all of the nice statistics that you can get with Istio. And then the last one in the chain is the router. And the router is what the filter that actually handles sending the request to where the correct destination, where it actually needs to go. And so given all of that, that's kind of like what we'll build on top of, because all of the security features we already touched on quite a bit with the TLS transport socket. With all of that kind of done, this is how we'll build the various components of Istio Security into the filter chain. So now let's take a look at the Pure Authentication resource. So at a high level, Pure Authentication is really what happens as far as like, how do I validate or how do I verify who the client that's trying to make a connection to me as a workload, right? So from the server side, right? If someone is trying to establish connection with me and in order to send a request, I have to verify who that is, right? And that's kind of the whole concept of Pure Authentication. This description comes directly from the documentation as well, but ultimately, right, Pure Authentication is configuring and controlling the level of mutual TLS, and in other words, how you can know or how you can identify who is trying to establish a connection with you. So in order to configure that, there is a custom resource that's called the Pure Authentication resource, and here's an example. And really, what you're doing is you're creating this Pure Authentication resource and applying it to specific workloads. By default, Istio is installed in permissive mode. We'll take a look at that here in a second. But when you want to change that, right, you can target it by creating this Pure Authentication resource and applying it to your mesh. And you can apply it at different levels. So you can apply it, mesh-wide, namespace. You can go down to a specific namespace. You can even go to a specific workload in that namespace, and even further, you can go down to a port level configuration if you need to. And the most narrow scope takes precedence. So this is important because if you have a mesh-wide config, and again, kind of the default config is permissive, you can have you can go more narrow and say, okay, I want to do this one namespace to strict while I leave the mesh-wide config at permissive, for example. So again, permissive, we haven't really fully defined it. We've talked about it a little bit. Permissive mode means that workloads can accept both plain text and mutual TLS connections. So in other words, if you have a service-to-service call, and that service-to-service call is two workloads that have sidecars, you're going to get mutual TLS even in permissive mode. And that's really cool because you don't have to do anything essentially to get mutual TLS, right? If you have sidecars if you have workloads that have sidecars communicating with each other, even in permissive mode, that will automatically happen over mutual TLS. But that also means that legacy clients can still work in permissive mode. So if you have an application and you have it injected with a sidecar, a client that doesn't have a sidecar can still interact with the workload that does have the sidecar. And so that's useful from an introduction perspective. It's useful from an onboarding perspective. But that being said, it's much less secure, right? Because you cannot validate or you can't verify who's actually connecting to you as a workload. You cannot enforce things as far as like, I only want specific services to be able to talk to me. So, permissive is great, and permissive is important as far as like migration. Like, if you're onboarding into your service mesh, again, it's kind of, we're talking about a journey, right? So when you start off having permissive mode makes sense, but your goal should be to get to strict. You should have a plan to get to the strict where everything has mutual TLS. Again, strict is mutual TLS is enforced. So in this case, there's no legacy clients. Everything has to have essentially a sidecar or has to be part of the mesh in one way or another in order to get an identity, in order to be able to talk to any of the workloads that do have sidecars. You can also turn it off with disable mode if you need to. And then for completeness, there's also unset, which means inherit. I actually have not really seen a lot of use of unset, but it is an option, so it's included here as well. So again, we've been talking about kind of scoping, right? And so this is kind of like what it looks like. So when you can have a mesh-wide policy. And so in this case, we have a Pure Authentication resource that is defined in the Istio system namespace. And in this case, there's no selector. So we'll take a look in a second what that looks like with the selector. But in this case, there is no selector. And since it's defined in the Istio system namespace, that's kind of the root namespace by default. So when you have a peer authentication resource that's in the root namespace that doesn't have a selector, that means it's mesh-wide. And so in this case, we're turning on strict mode for every workload in the mesh. Then you can scope it down one level further and go to the namespace. So in this case, we have a peer authentication that's strict, but we don't have a selector, but the namespace is foo. So we're not actually targeting the default configuration, the root namespace. We're targeting a random user namespace, more or less. So in this case, that means that apply to all workloads, but only in the namespace that we define. So you'll have a strict mode enabled for sleep and HTTP bin in the foo namespace. And then finally, you can scope it down even further to, I shouldn't say finally, there's one level lower, but in this case, you can scope it down to a particular workload. So in this case, we have a foo in the foo namespace. We actually are selecting based off label selectors, the HTTP bin application, and we're turning on strict mode specifically for that workload only. And then finally, you can go one level deeper and you can, so in this case, what we're doing is we're disabling mutual TLS on a specific port of the HTTP bin application, right? And this is useful if you have kind of some, legacy application that has certs built into it or something like that, where you want to keep that functionality in place and you don't want Istio mutual TLS to take over. This is a useful tool for that. So one of the components that is responsible for building up the security features in Istio is the Istio authentication filter. And so this is an HTTP filter that's built into, it's automatically added to your filter chain. So remember earlier we were talking about the filter chain match and selecting the appropriate filter chain. When you have Istio mutual TLS enabled, which is pretty much always, when you do that, you'll have this Istio authentication filter in your HTTP filter chain. And so in this case, right, where we have it outlined here, where we have the Istio authn filter in our HTTP filters. So as a request comes in, one of the filters that will process it at the HTTP level is the Istio authentication filter. And so what this is an example of what the config for that actual filter looks like. The config isn't too interesting. Really, we're just saying, there's a policy and we do peers by mutual TLS, more or less. And then there's also the skip validate trust domain. We're not going to go too into this, but it's just called out here for completeness because this is what the config looks like if you were to look at the config for your Istio authentication filter. So what this filter itself does is it will validate that the connection uses, and this is in strict mode, it will validate that the connection uses mutual TLS and that the peer, or in other words, the client certificate is a valid SPIFFE cert. And then more importantly, I don't want to say more importantly, but one of the other important things that it does is it saves the peer data for use in later filters. So, with this filter in place, with strict mode on, you'll get the validation of the peer cert. And in fact, you kind of get that for free already with the transport socket config we were looking at earlier, but this provides another layer to that. And then the saving the peer data, we'll take a look at this right now. So this is an example of the debug logs as a request flows through a proxy that has peer authentication turned on to strict. And the client is sleep and the server side is still HTTP bin. So you'll notice that the debug logs for the filter are setting, they call out, so even up here, not highlighted, we'll call out that we're validating X509 cert, we're in the mode strict. And then we're calling out that the set peer from the certificate is this cluster.local ns foo sa sleep. And so this is really the identity of the peer. And then what we're doing is we're setting the principal from that peer. So based off the certificate that was presented to us as a workload, we will look at the cert that's presented and pull out the identity from it. And so this is that SPIFFE identity that corresponds to the trust domain, which by default is cluster.local, the namespace, which is foo, and the service account that's running the workload that made the request. So the sleep service account, because the sleep service account is what's running the sleep application. And then you'll see that we're also calling out that the filter is going to save some of this dynamic metadata. And so we'll look at this here in a second, what that actually means. But you see that the source.namespace is foo, and the source.principal is this cluster.local namespace foo, service account sleep. So what happens is dynamic metadata is an Envoy concept or feature that more or less allows you to pass data from the various filters in your filter chain. And in this case, what we're doing is the Istio Authentication filter is going to save off that authentication data, right? So the source.principal is that identity we're talking about, and the source.namespace is foo. And this is going to come into play in the next section where we look at authorization policies. So let's go ahead and take a look at the authorization policies. So more or less, authorization policies are really just how you can do access control, right? So based off of the identity, either from the source workload, so the service that's calling you, or even on the request, you could do authorization. So we didn't look at it, but you can also do things like based off the JOT that's on a request, let's enforce access control on the identity of the request, which is contained in the JOT, for example. But yeah, so authorization policies allow you to do access control. So the authorization policy resource is what controls that. What you really get here is like, so you're writing your access control rules, and you do so by targeting a workload, which is what the selector field does. The action is either allow or deny. And in fact, in Istio 1.9, there's introducing a new concept of a custom action, which allows you to do kind of custom logic rather than just either allow or deny, which is, that's very powerful, and that will kind of open the door for some more advanced tooling on top of Istio. And then you specify the rules. So things like from, what's the source of the request, the to, like what are you trying to do in the request? And then there's another field that's not outlined here in this example, which is the when field, which allows you to kind of build out custom conditions if you need that kind of logic. But so in this case, right, we're allowing requests that come from the namespace foo, the sleep service account. So in other words, the sleep app, and that source, that principal, can make get requests to our HTTP bin application. So the authorization policies work in a way that's called, what the documentation calls out as implicit enablement. So in other words, you don't have to do anything to start using them. When you don't have any authorization policies present, everything works normally, right? There's no access control going on. But once you create an authorization policy, then it starts working. So once you have an allow policy in place, everything that's not explicitly allowed gets denied. And then you can even build on top of that, and you can actually, create deny rules, right? So if you have a deny and an allow rule, the deny rule, all deny rules are evaluated first. So the deny rule will be evaluated first, and then the allow policy all of the allow policies will be run. And again, if there's anything that's not either explicitly denied or allowed, once you get to the end of that kind of chain, right, or that list, then everything else is denied once the allow rule is present. So kind of based off of that, it's a little confusing. One of the best practices is to have, when you want to use authorization policies for access control, to use the deny all rule. And this kind of simplifies the mental model, because you know that this rule is in place. So no matter if you have any allow policies or not, everything will be denied by default. This is a little bit of a commitment, right? Because this means that every access control rule has to be explicitly created in order to allow traffic to flow from what actually needs traffic to flow. But it does kind of give you that fail safe that that no matter what happens, there is that catch-all rule that will deny everything. So kind of going back to what we were looking at, authentication policies, authorization policies can kind of be scoped as well. So this is an example of the deny all rule. In this case, it's in the default root namespace with no selector. So this is a mesh-wide config, right? And so in this case, we're doing the deny all rule for all of the workloads in the mesh. And then similarly, you can do a namespace specific config. So, no selector, but it's not in the default namespace or the root namespace, it's just in a user namespace. And so this will apply to all workloads in this namespace. And again, this, the selection is for the target, I should say. It's kind of hard to reason about, but you're targeting a workload, and that is the workload that's the destination of traffic, essentially. And then you can also specifically target a workload only, right? So in this case, we're targeting by the HTTP bin app through label selection in the foo namespace. Yeah, so then how is this actually enforced, right? What actually happens to do the access control, deny or allow, right? What actually happens as far as the enforcement? And so that's what the way this is implemented is the Envoy RBAC filter. And so this is kind of an example of the RBAC filter configuration that gets automatically generated based off of the rules that we were just looking at, right? So, again, this is in the filter chain, right? So we have the Istio authentication filter that we talked about, and then now we have the RBAC filter in place. And so this is, the config. Let's take a look at what this actually does. So remember that the Istio authentication filter was saving off the authentication data or result of the authentication to dynamic metadata, right? So going back to what we had, the source.principal in the dynamic metadata associated with the Istio authentication filter was this cluster.local namespace foo service account sleep. Then this RBAC rule is going to check, the principles that are allowed essentially is, that does some and or type stuff this is in place so that you can build out, kind of complex rules or policies. But in this case, we have a very simple one, which is saying that, we need it to be sleep in order to be allowed, right? And so the RBAC filter is then going to check that in the Istio authentication metadata, the source.principal is an exact match with that sleep workload, right? So the trust domain is cluster.local, the namespace is foo, and the service account is sleep. And since that is what's present in the dynamic metadata of the Istio authentication filter, the RBAC filter is just checking that, right? And in this case, it's checking that it's an exact match, and it is. So now the request is allowed. And so that's how the enforcement of the of the authorization policies actually takes place, is by this Envoy RBAC filter. So finally, let's take a look at access policies in Gloo Mesh. So access policies in Gloo Mesh are essentially, you can think of them as authorization policies. Really, you're writing policies that say, I want to allow traffic or communication from a source workload to a destination workload. And that's what the access policy is. One thing I will call out is that this section here, this sentence right here, where we say on the virtual mesh, your user can specify a global policy to restrict access and require users to specify access policies in order to enable communication to services. So, this is not going to go into the full weeds of how you use Gloo Mesh, but the Gloo Mesh has a component of a virtual mesh, and that's exactly what it sounds like, right? It's a virtual mesh made up of several other meshes. And this is that global access policy that is called out here in the documentation. So it looks like this, right? Global access policy is enabled. And this is essentially more or less what that deny all rule does. So when you have this global access policy enabled, what you're doing is you have the deny rule in place kind of automatically. And now you can build out your allow policies through the access policy resource. So this is what the access policy resource looks like. And so again, you're talking about sources and destinations, right? So, this is kind of so it does get translated back to authorization policies in Istio, but this is kind of a higher level view of that, right? So in this case, we have a source selector, and in this case, our source selector is a service account reference, and that service account is the sleep service account that's in the foo namespace. And then what's kind of new here is that the cluster name is specified, again, because we have the concept in Gloo Mesh of multi-cluster, right? That's kind of built into the tool. So you can specify which cluster you're talking about. And then you have a destination selector, which is selecting which this is the target of the policy, right? The destination of the policy. So the sleep service account in the foo namespace in cluster 1 is allowed to talk to the HTTP bin application in the foo namespace, right? So what that kind of looks like is what actually happens is that you have this access policy that we just created. We apply it to the management plane. The Gloo Mesh networking component specifically is what's looking for it. And then that gets translated into the actual authorization policies that are translated from the access policy. So kind of more specifically, right, here was the access policy we were just looking at, where we're saying the sleep service account in the foo namespace in cluster 1 can talk to the HTTP bin app in the foo namespace, right? That access policy is applied to our Gloo mesh management plane, and then the Gloo mesh management plane is responsible for creating the authorization policy that corresponds to it. So in this case, we're creating an authorization policy in foo, the foo namespace, for HTTP bin, and then the source is the cluster 1. This is kind of a new thing, right? This is, since we have multi-cluster, the trust domain is not going to just be cluster.local because you have several of those, right? So you need to have identity. Identity kind of extends to the cluster as well. And so in this case, the trust domain is cluster 1, right? So that's where this is used. And then it builds out the principle how we already have looked at just with plain Istio, right? So the namespace is foo, and the service account that runs it is sleep. So this is kind of how that translation occurs. So kind of looking at it from a higher level, right? We have 2 clusters in our virtual mesh, right? And we have a management plane for Gloo mesh. And so as a user, I'm going to create this access policy that we were just looking at, right? So I apply this to the management cluster, or maybe this is a CI/CD pipeline, whatever, right? It gets translated to the authorization policy, and that authorization policy is applied to the 2 clusters that make up the virtual mesh. And so again, our access policy was for cluster 1's sleep account, right? So this authorization policy that's created is not going to allow sleep in cluster 2 to make a request to say HTTP bin in cluster 2, right? So the sleep pod or the sleep workload in cluster 1 can talk to HTTP bin in cluster 1 and in cluster 2. And so that's kind of intentional, right? Because the services or the service accounts that are in the various clusters, that, like I just said, that the identity now will include the cluster. So now you can create complex or compose, complex access rules that are based off of the cluster topology in addition to just the service namespace topology. And so, this is a kind of, we'll use this example again, right? So this is kind of a refresher, right? We have the sleep service account in the foo namespace in cluster 1, and the destination is the HTTP bin app in foo, right? And so this access policy will get translated to the authorization policy we were discussing in both clusters. But you can even go a step farther, and you can kind of scope down, similar to how we do in just plain Istio, you can scope the clusters of the destination. So in this case, what we're saying is the sleep app or the sleep service account in cluster 1 in namespace foo is allowed to talk to the HTTP bin app in namespace foo in cluster 1. And so in this case, the management plane is going to create this authorization policy, but this authorization policy is only relevant in cluster 1, not cluster 2, because there's nothing that can actually access it in cluster 2. And so the management plane is responsible for kind of figuring that out and kind of building out the authorization policies based off of that. So you can kind of see how this allows you to compose, very complex rules that kind of express pretty complex security requirements because you are operating in a multi-cluster world, right? And so with that, we'll kind of call it a day. I hope that was useful. And if you have any questions, please let me know. Thank you.